All right, good afternoon to everybody. We're continuing with our sound session today, and very pleased that Ali is here. Now he's on the podium. You're welcome to ask lots of questions. I'm saying this straight ahead, okay? You have an unlimited account of asking questions. And Ali used to be Surrey, and now he's Quick. Sorry, he used to be at University of Surrey, and now he has Quick in Qatar. It's a research center in Doha, a very quickly growing research center, actually very similar to CTTC, with the same mission, bridging at academia and industrial world. So he's right now there involved in broadband projects. Before that, he did his PhD and master with Rahim Tafazuli in Surrey University, working on, surprise, surprise, self-organizing networking. So we have the professional right here, and we're looking forward to a long and self-contained presentation on SON. Ali, the floor is all yours.
Thank you very much, Misha, for your introduction. Okay, so can everybody hear me? Okay, that's fine. Okay, thank you for leftover audience and being here today. Okay, so this presentation is actually a tutorial combination of tutorial and a little bit of technical insight into some SON solutions. So I would like to have it in a more of a discussion session than just a one-way presentation. Okay, so this is the layout of this presentation, in which first part is introduction, in which we will address the basic questions, although Misha has gone through them, but redundancy is sometimes good for more deeper understanding. And in the next part, we will discuss about the desired characteristics of self-organization we want in cellular systems, and also some taxonomy we can have to classify different types of self-organization solutions and systems. Okay, then in the third part is actually a review of what has been done so far, consisting of 4 different regimes: standardization, projects, open literature, and also some overview of industrial products with SON capabilities. And in the last part, I'll go deep into some of the sample solutions which enable SON can enable SON into cellular systems, and concluding with some open research issues in this area. Okay, to begin with, what is self-organization? A big question. Nobody knows the answer. Means if we go back into the history, means I think as far I could dig down, the philosophical definition first heard about self-organization was by this guy called, I'm unable to pronounce, but Rini. And he was a philosopher, and he realized that it's not necessary to design everything. Sometimes you can design something which can later emerge into something different. So it means the inspiration is from nature, means God could have arranged the thing to emerge from what he had created if he did not want to create everything by himself. So this is the most abstract definition you will ever find, but this is unfortunately the first idea of self-organization you will find in literature. So in more scientific terms, self-organization is intrinsically a nature-inspired phenomena, and its applications to man-made systems started about half a century ago by Ashby in cybernetics, and then it moves to thermodynamics and some chaos systems in physics and complex systems. And finally, it made through to ad hoc networks and sensor networks about a decade and a half ago. In cellular system particularly, its application or its kind of use started, means the first person who conceived that there is a need of self-organization in cellular systems, or we can make cellular systems self-organizing, is Spilling, who published a paper in 2000. And this paper was kind of more of identifying the needs and opportunities to introduce different SON functionalities. but exact definition is still missing and it's specific to context, but to our purpose, old definition in cellular systems is can be found in Prehofer's paper back in 2005 when he tried to define it like a system is said to be self-organizing if its behavior, if it can organize itself without any external or central control entity. This is debatable definition, but still it is a definition which is there in literature. But to have a more kind of characterizing definition, we need to really look into nature from where this phenomenon is coming. There are a number of examples, as we all know in nature, which there are a number of systems which behave in a self-organizing way. If somebody doesn't know, then I can explain a little bit here. For example, shoal of fish. You can call it school of fish. This shoaling behavior of fish is interesting self-organizing phenomena, and in the same way, even often you see flocks of common cranes flying in the sky, and they also exhibit self-organizing behavior. And swarm of insects is also a self-organizing system in nature. And interestingly, there are some common properties in all of these systems which can help us better to understand about them. For example, the first property is you would be unable to find a central control unit in these systems. Means you won't be able to identify a leader fish in the thousands of fish. You won't be able to identify a leader bird, or you won't be able to identify a leader insect. But still, they are behaving in a kind of coherent way without a leader. Second thing is, although they are not physically connected to each other and neither they have a intelligence to the level that they can communicate globally with each other throughout their flock or group, but still they have, as a whole system, they have a high degree of maneuverability, which you can term as agility. Means, for example, this fish here, I'll show in some later slides, a shoal of fish here has a capability to change its shape, avoid sharks, avoid kind of any hurdles, and search for food collectively. And similarly, this flock of birds has a capability to maneuver as a system without breaking apart. And all this still without any obvious control. And then stability means, apparently in physics, when people study such a system, it seems to be perceived that it should be on the edge of chaos, or it means they are almost chaotic system. But apparently in nature, we hardly observe any chaos in self-organizing systems. So we see that stability is also an intrinsic property of self-organizing system in nature. So based on these
observations... Can I ask a question to the one before? Please. Yeah, I mean, I'm not sure how you see the definition of Christian, but to me, this is like saying the world is beautiful because the world is beautiful. It's not really a definition. He says
it's not definition.
It's not at all. He says a system has a property of self-organization if it organizes itself.
No, means this is, as I mentioned, it's not, as I said, it's not a characterizing definition. It's a just observation-based definition. And to have a characterizing definition, we are going through the case studies.
No, I very much like this down here, because that is really somehow characterizing the properties of. But this one up here, which has been cited 10 million times, and I've been discussing it with Christian. It's not a definition. It's a. It's two equates to two statement.
Yeah,
right? This is what it is.
I agree with that. But the thing is, since it's a tutorial, and this is a paper back in 2005, which was on self-organization, and its name was Paradigms for Designing Self-Organization in Communication and Principle and Design Paradigms. And it claimed to be at least kind of giving some definition. This is not in inverted commas there. Even he is not claiming it to be definition, but this is the sentence you will find in that paper, which at least tells you that what self-organization. Otherwise, you will find that paper without a concrete definition of self-organization. So this brings us back to your comment in the morning that people have been working on this area for decades and still we are missing a definition. And that's why I'm going into detail.
No, this down here is fantastic.
Yeah,
Yes.
to understand that if we want to define it for our own purpose, how we can define it possibly. So recently we published a paper where we tried to define it, but still I'm not confident this is a definition which make everybody happy. But at least based on the previous case studies and observation, and also incorporating what Misha said in the morning, means more agreeable definition. Adaptive or autonomous function in a system is said to be self-organizing if it is scalable, stable, and agile enough to maintain its desired objectives in face of all potential dynamics in its operating environment. It's a long one, but it at least tries to encapsulate what a self-organizing system should be when we are saying that, okay, its future cellular system should be self-organizing. So that means if you want to break down this definition, this scalability, stability, and agility is coming from the observations, and it's not, they are not kind of necessary criterion, but they are desirable. But the necessary thing is that it should be able to maintain its objective. System should be able to maintain its objective despite the fact its operational environment keeps changing. For example, here, means it should not be like that. Okay, this shoal of fish is maintaining itself when nobody is around, but when a shark comes, it breaks apart. So then it will lack stability. So it's not meeting its objective. Which objective, for example, in this case is, we'll go into more detail in one of these case studies, and then we'll see that what are the mechanisms which result in the emergence of this behavior. Okay, so we're done with little bit with the definition. We'll get back to come back to this when we'll go towards design. So the question is, why we want self-organization? It has been kind of answered in the morning, but I'll add some more points. First of all, money matters. Nobody can disagree with that. This is the crucial factor. How self-organization will help us to save money, and I'll go in detail later. Growing number of nodes, heterogeneous networks, means future cellular networks are not apart from this mess. Means they are going to be like this, not in terms of different sizes of cells and nodes, also in terms of technology. Means GSM, LTE, UMTS, and Wi-Fi. And this one is the most important thing. This addresses one question which was asked in the tea break by a colleague, that okay, means this need for adaptation and need for making cellular systems smart was already there, so why to invent a new term? The problem is, if you look at the literature and history of communication system research, you'll see that most of the energy has been focused on noise, fading, fast mobility. And if something, when some people got out of this limited scope, they went at the most towards pop-up hotspots or slow user mobility, temporary shadowing. But if you look at these variations, which are a reality, a cellular system goes through all these different kinds of variations through its life cycle. You'll hardly find a piece of literature which tries to, for example, provides you a solution when an operator has to change its operational policy for them because it's not able to pay energy bills anymore, or users' expectations have changed because another operator came into the market, or seasons are changing. Okay. With the seasonal variations, a lot of stuff happens. I'll go into detail later. And this requires a change in the operation and design of the cellular system. But unfortunately, our first priority when cellular systems came into being was just provide coverage with voice telephony. So nobody really thought about that they will ever had the need to adopt themselves. So design is semi-static, but ecosystem is very ruthless and it's very dynamic. Increasing complexity, very obvious, with 3 different technologies, 4 different technologies to operate. So these are, means if you put in a nutshell, this is why we need self-organization, but we'll go into detail. Okay, why does means what's the money issue? Means okay, data is growing, but so is the capacity. So what is making us worry? The problem is the applications you see means they are mushrooming up like I would say weeds. Every single second you see 10 more applications are born, and they are only limited by imagination. But cellular system or wireless systems capacity is kind of very hardly bound by physical limits. And for existing cellular system, including UMTS, these physical limits means we are already at the breaking point. So yes, that's why LTE is there. So will LTE help us? Yes, if we want to play the need for speed, yes, it will help us. How? Yes, in terms of speed means that we would be able to perhaps meet user requirements for a few years more, and we won't have much complaints. But the problem is much beyond the need for speed only. The problem is actually total cost of ownership is not adding up with the revenue. Well-known fact, but the reason, sometimes the reason behind is neglected. The reason is not that means I was discussing it with my colleague that okay, operators are in trouble. For example, in UK, the annual revenue has gone down by 1%, and the data which goes through the network has gone up by 30%. So this is a problem. So the comment was why operators don't charge higher rates there to their customers. There are two problems with that. First of all, with the in competition, multiple operators in the market, the churn is not in the favor of user churn is not in favor of any of the operators, because you cannot plan your network smartly enough if you don't know how many customers you gonna retain. If customer changes, it's a service provider. It's not good for both of the operators. The one who lose it, he planned his network assuming he would stay with him, and no, he gonna pay the operational cost for that user. And the guy, means the operator who got it, did not plan his network that I'll get this new user, and would be unable to provide the quality of service it should provide. So, and also the second problem is with these new applications, which are supposedly a smartphone application, but sometimes they are not really smart because they keep active, they stay active. For example, if you talk about Skype or even some very silly application, particularly in LTE is there in Japan, and KDD has to shut down their whole operation because of one single application. And you cannot imagine how silly it was. It was just a time teller application. Means every time you click a button, a beautiful lady with a picture with a slate will tell you what is the time now. And this single application killed the KDI, and they have to kind of ban this application. So, and at the same time, energy applications. Yes, when I gave this example, somebody actually I thought this is not a wireless communication problem; it's a psychology problem, but it's a fact. Okay, energy bills are going up, so as a result, this is the dilemma, and this makes operator look like this. They are worrying about their future in terms of money. So this is how money matters. So the problem is average revenue per bit is dropping. Sorry, there is a mistake. It should be average revenue per bit, B, not U. Okay. So will LTE help us? If you look into details, not exactly. It's a harsh statement, but based on the forecast, this is what people are estimating. Means $8 billion capex over the first 3 to 5 years, 30% to today's OPEX. Smaller cells are inevitable because of the higher frequencies. And on top of that, we have 3 different technologies to manage because operators want to preserve their investment they have already done in the previous technologies. And all IP is a very good thing, but yes, you have to keep the active control plane always active. So in that context, actually means there have been questions why femto-cells, Wi-Fi is there, why we need femto-cells. So I see femto-cell as a rescue mission for operators, and they are the main drivers behind it. If you go dig down, it's the operators who need femto cells, not the users. And the reasons are obvious based on my previous slides. So, and since operators need it, so vendors have to sell their equipment to operators, so they have to kind of push the research for that, and we get money from either vendors or operators. So this is the bottleneck. Femto cells is a reality. How it's a rescue mission. These are elements. These are the steps which are hard steps which a typical operator has to go through to provide you mobile phone service. Means it starts with the survey, expensive, labor extensive. Planning, you have to buy expensive and sophisticated planning tools. Means you input your service data into planning tools, and this planning tool tells you a deployment plan. You send your engineers, they install base stations, and then you send your more smart engineers, they configure and commission base stations. And then it comes to operation, and then you have to always remotely monitor your network, and also you have to do some in-field measurements off and on. I think you understand why we need in-field measurement. Amisha in the morning explained that not everything can be remotely monitored through planning tools or some prediction models. Okay, so then based on those measurements, you need to recalculate your parameter, and then you have to send another kind of engineers to do the manual optimization of parameters. And if something goes wrong, then you have to go through the 3 steps on the right. So what is going to happen with femto cells? No need of survey, no need of planning, no need of deployment engineers, no need of commissioning and configuration engineers, no need of in-field measurement, no need of manual optimization, no need of problem diagnosis, no need of compensation, and no need of installation. But
problem diagnosis?
There is a big if femtos are equipped with SON.
All right, I see. Okay.
Okay. So there is a big if and only if femtos are equipped with SON. So the story is we need femto, and for femtos we need SON. Okay. So is the problem solved? Yes, it seems problem is solved. Yes, low energy consumption with femto cell, no planning cost, no deployment, blah blah. All of the problems seem to solve, but
here is okay. You will solve all these problems here if you assume that you are implementing self-organization networks in all the planes. I mean, for self-configuration, self-optimization, or self.
I'll come towards that
healing.
later.
Okay.
Yeah, of course.
Okay, so
I said femtos are equipped with SON. SON means self-organization. Self-organization further contains self-configuration, self-healing, self-coordination, self-optimization. I'll go to
okay, this is a huge challenge.
Yeah, it's a huge challenge. Means that's why I put static. It's like a marketing strategy. You put the most difficult condition in the bottom. So if femtos are equipped with SON, so even with yeah. Okay. So means it seems that femtos are a rescue mission, and they are really the gonna make our life easy. But if life was so easy, then nobody have ever thought about heaven. Problems means it's not only the femto cells which have to have SON. If you put femto cells in your network, you need to have SON everywhere in your network, even in macro cells. So you solve some problems, you created some problems. So what is the something more? Means we need something more. In addition to these femto cells, we need something more. And to understand what is this something more, let's summarize our problem. Suboptimal performance and increasing cost. Anybody has a question at this point? Means on the suboptimal performance, means there are many solutions in literature for optimal performance, but still cellular systems are operating on suboptimal performance. If anybody has a question about that, then I can go into detail. Otherwise, I'll assume that you understand why cellular systems are still operating on suboptimal performance. Okay, let me give you an example based on my bitter personal life experience. About 5 years ago, it was 5 in the morning or 4 in the morning, December, winter. And I was with the operator back in Pakistan, and I received a call from my manager that, okay, a site has gone down and we are receiving complaint alarms. You need to go and see what's the problem. Okay, so what was the problem? I went on the site, I saw that, okay, the microwave link. This is base station RF antennas to provide coverage here. These are working fine, but the microwave link to another base station, which was actually BSC, base station controller, was not working. I was unable to detect a transmission between the two. It was working till the last night, but it is not working anymore. So all of this area, which is very critical area, is not being covered because people are not able to connect back to BSC. So with all your theoretical solutions, there means nobody thinks about this kind of problem. So means I had to kind of spend almost 18 hours, and finally I figured out the problem was there was a large water body here, and the guy who surveyed this area, he did it in summer. Okay, and in summer this water had a different reflection index, and in winter this water has a different reflection index. So it took me 18 hours to figure out, because I have to drive through all the way and to see, and then call for another equipment to measure the reflection index, and then it turns out this is the problem. So, and you can understand that means for an engineer, means I had almost 10 people with me. So this was a team of 10 people who has to mobilize with this 20-kilometer range, checking every inch of space, what is the problem. And then, so this is one of the reasons. From operator's point of view, as Misha said, that means we don't care the network is there or not, as long as the service we are getting. But once the service we are not getting, means so these kind of reasons, there are many reasons. I can give you a lot of interesting stories from my experience, and that's what motivated me to do something like this. And users don't care what time it is, but they expect it to be running 24 hours. So suboptimal performance from users' point of view. And increasing cost. Of course, when you have problems like this, which you often have, there are multiple reasons. Don't want to list them, but I can discuss if you want. Then you will have a huge operational cost. And the reason cause for this is dynamic, range of dynamics. As I showed you, the circle base means this is the dynamic which a system has to go through. Means this thing changed. Okay, semi-static design. Again, this means what I had to do is I had to just tilt it up by 1 degree. So this was the solution. So, but I had to come and do it manually. Means it was unable to figure out itself. Okay. So increasing cost is because of these 3 reasons. We need manual intervention. This is a big problem. Okay, so how we can countermeasure these problems? It brings us back to some terms which we have already seen. We need adaptability, we need agility, automation, and scalability. If you see, you can see some one-to-one correspondence between them. For dynamics, you need adaptability. For semi-static design to cope with that, you need to bring in some kind of agility. And for increasing complexity, you need to automate the whole process. And to remove the manual intervention also, you need automation and scalability. So that's why I said this is more kind of the definition we proposed is more functional oriented, means what we need actually. So that brings us to the same point. We are back to just to emphasize that when you start working on self-organization, what exactly you should be looking for. It's autonomous, adaptive behavior. We should not compromise on these 3 characteristics. Okay, So what is happening? I mean, I have given you a practical example, but just to put me, because people would be seeing the slides, to put it in a more kind of graphical way, typical cellular system network cycle means the previous slide I showed you was telling about the whole life cycle of the cellular system. Now we are talking starting from the point when the cellular system is up and running. Okay, once the cellular system is up and running, this measurement process has to keep going all the time. It can be user based. In the current networks, only few user reports are collected because they are almost not usable. Drive test based measurement, and this symbol show that time consuming and labor extensive. And this is not kind of, you cannot hire a actual labor, you have to hire an engineer with white tie. You have to pay a lot of money to him, he has to be a skilled guy. So you make a database and then you have to hire some smart people to do the performance analysis, or you have to buy an expensive tool for doing a performance analysis, and then you calculate the optimal parameters which are now optimal according to the recent state of your network, and then you send some engineers and they go back. Either they remotely configure if some parameters are remotely configurable. For example, in modern cellular systems, there is electronic antenna tilt, so they can probably remotely configure. But for some parameters, you have to go physically in the field. So you see what we are losing here means we are actually losing here time, money, and also there is one hidden loss here. The hidden loss is suboptimal performance. Means you would say, why suboptimal performance? We are doing it manually, but still we are optimizing our network. The problem is, by the time this guy goes to the tower, he will adopt the parameter, and then he come back and he'll have another call from his manager that you need to go back. The problem is the time this whole process took. Meanwhile, so your cellular network has already changed. There has been the plaza has been built, the vegetation grew, or maybe autumn came, so there is no vegetation anymore. A lot of problems. So due to this delay or latency of this cycle, current cellular networks are bound to operate in suboptimal performance. It's an understood fact. Every operator knows it, and they live with it. That's why I put in the title, "A Dream Come True for Operators, Self-Organization." Okay. So how the SON will benefit? Very simple. You're going to save some money here. 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 And to put it simply, self-optimization loop will look like this. But this is what means dream. So far we are on the dream. We need to realize it. But when you're dreaming, you want to enjoy it. So, so what kind of figures operators are looking for? There are some reports. To understand that, we need to understand the total cost of ownership for a cellular network in terms of operators. 70% of the cost is OPEX over the life of cellular system, which is counterintuitive. You think that you have to invest in the beginning. But for cellular system, 70% of the cost is OPEX and 30% is just CAPEX. And according to some detailed analysis, you have to buy this for very expensive fee, this report. Anyway, this is the courtesy of one of my friends, by the way. Anyways, so the figures tell us that means we would be able to save almost 35% in OPEX and 15% in CAPEX. There are some forecast analysis based on these are the components of OPEX which would be affected, which can be affected potentially by SON.
Which one? The one you...
Manpower.
The manpower, can you get rid of
operation,
that? All right, okay.
Site rental.
Why site rental?
This is site because at the moment we have to plan very carefully. It's being assumed that once you have a SON operation in place, you can let loose. You don't have to buy rent a site which is the top of the city or maybe a very high plaza.
But do you really think this will happen? I think with the site optimization, because it's so expensive,
No,
they are pretty. They're
no,
pretty
actually,
good.
at the moment, the problem is when the site acquisition itself has multiple cost components. It depends. Means if you, because sometimes because of the optimality, you don't want to change the location by even 5 feet, because later you will have problems. But with a slight location variation, maybe you are able to buy a next building which is cheaper or next area. So means it's based on real figures. For example, 70% of the base station in the urban area are on prime location, because they have to stay on the top of a building or bank or some place for which they have to pay a heavy rental. And also the energy consumption. Means if it's on a commercial place, you are paying commercial energy bills.
Well, as far as I remember, because I was involved very heavily in optimization tools with site optimization, etc. You get a set of locations where you can put the base station. So you can't put it everywhere. You have a little bit of flexibility.
And you always have,
yeah. So I think on site rental, I would be surprised if you could squeeze this a lot. But yeah, the manpower probably could go down, the operations could go down, and you're saying that the power could also go down.
Go down. Means actually, I have just, as I said, using this figure. This is the actual analysis by Inset.
Right. Yes.
So means they might have done some calculation based on real matter, because they sell it for I think $3,000.
No, that's very interesting. The numbers, yes.
Yeah. So there is an alternative figure if we were interested. Means IGR forecast is saying that we will have a saving of 2.34 billion
in dollars. Okay.
In dollars in US. So these are the numbers. So what exactly it means, to summarize, what is the relationship between FEMTOs? FEMTO is a rescue mission. We need FEMTOs. It's not a choice anymore. But when we have FEMTO, SON is not a choice anymore. It's a necessity. And once we have FEMTO, macro should have SON as well. And the agenda behind is very clear. Profit maximization, quality of profit means actually we say that, okay, we want, as a researcher, we want to enhance quality of experience, but quality of experience actually should give us some profit. That's why we want to enhance it. So profit maximization is the main driver, and it can be broken down to further things. Energy efficiency, for example, one of them. Okay, enough with the introduction. Let's go back towards how to design self-organization. As I mentioned, intrinsically it's a nature-inspired phenomenon, so it's good to look at nature first before doing anything else to see if we can get something out of that. So biomimetics. Biomimetics is a branch of science, I think everybody knows, where we try to mimic the natural systems to come up with a similar solution or efficiency in our man-made systems. It can be further broken down into direct biomimetics. The example is design of aircraft wings, radar, camera. This camera is based on eye, radar is based on bat, design of aircraft wings is based on birds. And this particular picture here, somewhat means everybody understand what is that? Oh, yeah, fish, cool. Yeah, and this guy means it's scaring away this guy by behaving, means by looking like as if it's a big fish, but it's hundreds of very small fish. Okay, in direct biomimetics, we don't exactly try to copy the natural system, but extract the abstract principle, and then we tailor it according to our own application. I'll go into the design methodology later at the end. Biomimetic approaches, that's what most of us do, means classic optimization. If you want to go into this is a non-exhaustive list, and classification is in our paper. Let me see. Okay, here you will find some more detail on biomimetic and biomimetic approaches, and I'll come back to design once I'll go towards technical contribution. Okay, classification of SON. Once we understand what is SON, now we need to have some framework to put them in different categories. First category is natural time scale based classification. different SON operations have different time scales. Objective-based classification, every SON operation must have an objective. Phase-based classification, cellular system have a life cycle of 3 phases: configuration, optimization, and healing. So first, the time scale based, coming back to the same figure, we can classify apparently into 4 categories: very short, short-term, medium-term, and long-term. And as I mentioned earlier, most of the, you'll see that most of the research has been focusing on towards the smaller time scale dynamics. Okay, phase-based classification, this is not exhaustive list, but 3 phases, and in each phase you can divide SON solution according to their objectives, what they are doing. Okay, I think I should rush towards the actual solution. So this is how overall SON system should look like. Means it should be self-configuring, and self-configuration features are already specified in CGPP, and this should be kind of able to do the load balancing. For example, this mobile move from here to here. So, and this is example of self-optimization, and this is example of self-healing. Something went down in this cell, and the neighboring cell has to be friendly. Okay. Some overview of the projects which are going. Means before the project, this is a brief timeline. As I mentioned at the beginning, started in 2000 with this Spillings paper, and then this paper by Prehofer, from which I got a definition. And then after that, means there are a large number of works on individual solution, which I'll go into detail later. In terms of standardization, it was triggered by NGMN. Again, it's a dream come true for operators, so NGMN was the kind of main driver behind it in 2006. Misha has already provided a list, so this is a more detail. I'll leave it in the slides, so if somebody wants to consult it. Actually, NGMN specified that what SON functionalities cellular system should have in each phase. For example, in deployment, what self-configuration functionality should be there, in optimization, what should be there, and similarly in maintenance and update, what SON functionality should be there. Okay, in terms of 3GPP, again, Misha has gone through them in detail. 3GPP followed NGMN and open literature. Okay, the projects. Since there was the interest by NGM and also by operators, so some projects started. And the reason I have put them here is if somebody is interested to see that what has happened, then they can go into the websites of these projects. These 3 projects listed here are more focused on SON solely, and these 3 projects. The first project is BeFEMTO-A. We are here for BeFEMTO-A. It's not solely focusing on SON, but as femto cells are kind of married with SON, so we have this project. But this universal self project is SON focused project again, and this is India UK ATC, means Advanced Technical Cooperation or something, in which they have SON theme as well. So these are the noticeable projects if you want to go into detail. In terms of open literature and self-configuration, the logical flow can be defined like this, but this is again not my, it's a protocol design, it's not my area, but I have put it here to understand means where you need to work. For example, scan neighboring, what are the steps which would be required to configure, self-configure the network. In terms of open literature, there have been a number of works on neighborhood relationship functions. They can be categorized into different areas. First, location-based, centralized. Central server knows the location of all the nodes, and it will tell every node, okay, this is what something Misha talk about. But since there was a need of SON, so people have started investigating some more dynamic and distributed methods. For example, this SNR measurement base method, where base station node will sense the SNR from different base stations, and then based on that it will decide that is it what are exact neighbors. But still there is a margin for improvement, because with this SNR-based distributed solution, the stability is issue. You are not always wrong, right, because of the shadowing. Self-optimization, again, this is the area where most of the work has been done on SON. Self-configuration is quite neglected. Self-healing is quite neglected. And I would just refer you to this paper if you want to go into details. This is the structure of self-optimization section of this paper. You will find a number of key papers in each of these areas which are discussed in this paper if you are interested in any of these self-optimization areas. Okay, self-healing. There are some papers which are listed here, but still there is a lot of stuff which needs to be done. Particularly detection is again, just like neighbor list configuration, detection is a tricky area and it needs some contributions. And if you want to look at the logical flow, how self-healing should work, then this is a flow chart. Again, I'm copying it from my paper. You can go into detail later. Actually, I want to rush towards the last part before you start sleeping. Okay, last two slides on this part. In terms of industry, it's interesting to know that it means the industry is a little bit, because since money does matter for industry, so they are ahead of standardization. For example, in 2006 or 7, Motorola launched the first SON base agent, and it sold it to its customers for UMTS. And now for LTE, they already have a release 3. And these are the key features which they have implemented. The noticeable thing about this SON agent they're selling to their customer is that since SON is a new thing and operators are kind of reluctant to rely on it because of many reasons, for example, machine learning, unreliability and stuff. So they have provided actually a review mode in their agent. It's not fully automated, it's automated, but before doing any operation, as Misha said, it will ask for your approval that I'm going to do this, please allow me. If you'll allow it, will do it. Next time it won't ask. So this is the review mode. And NEC went a step ahead. It just means they don't only ask, but they have coupled a simulator with their SON agent. And what does the simulator do is that means whenever there is a need for a SON operation to be triggered, it simulates it in the simulator and tells you that after this operation has been done in the real network, this would be the output. So you can actually see that, do you like it or not? Then if you like it, you can let it go. But there is a catch. Catch is that the simulator is unable to kind of always follow the real situation. So once you have done the configurations, if some of the configuration are manual, you have to come back and feed it into the simulator to keep it actually update with the real network. So to summarize, there is a margin for work on self configuration and self-healing, but you can also find some gaps in self-optimization as well. Okay, some SON examples. This is interesting work. Okay, as I said, I was bugged by this tilt optimization problem, and this is one of the tough challenges. As Misha said, means the operators don't like to anybody less experienced mingle with tilts of their antenna, because the problem is it propagates. So the first contribution I'm going to present is actually tilt optimization, autonomous tilt optimization, self-organizing solution for tilt optimization. Okay. Before we go into detail, here's a brief overview of what is done exactly on tilt optimization in literature. There are a number of papers you'll find in literature, but most of them are actually centralized solutions, which assume that centrally you'll at a central node you'll propagate the optimal tilts to all nodes, and then they are going to configure them. But the solution we are going to present is actually distributed, as I mentioned, it's scalable. Let's go into detail of that. First, the system model is very simple. I'll present this scenario for a macro user, solution for a macro user, macro cellular net scenario, but in the end I'll show a slide which you will be able to extrapolate it towards heterogeneous networks as well. Okay, what we got here? This is a multi-cell network, multiple base stations, and these small dots are showing users, and the small circles are actually kind of hotspots, which are natural, non-uniform user distribution. And each base station has a antenna, sectorized antenna, and they kind of have to optimize their antenna tails such that the spectral efficiency, average spectral efficiency in the network is optimal according to this user distribution, because the user distribution is not uniform and it will keep changing, so the tail need to be optimized. In classic networks, maybe Misha can help. How often the tails are changed? I think every 3-4 months, depending on the change in network. Yeah, yeah, but it depends. Yeah, if you are really having complaints, then you have to. Anyways, okay. So to solve this problem, I have used a hybrid approach, which is biomimetics and a biomimetic mix. So to understand how that approach works, I'm just going deep into one of the case studies, referring back to these flying birds. How does this self-organize? It's very simple, but at the same time impressive as well. They do only 3 things. Each bird actually do only 3 things: separation, cohesion, and alignment. Means how does it start? Means one bird starts flying, who has eaten the most, who's more energetic, and rest of the birds start following it, but they make sure that they are doing only 3 things. Means at least these 3 things: separation, cohesion, and alignment. They maintain a separation, they maintain alignment with the direction of that bird, long-term direction, and they also, when they are maintaining a separation, they don't kind of split apart. Still they are cohesive. It's like cooperation and competition. They maintain a cooperation and competition at the same time.
And I don't understand the difference between cohesion and separation.
I mean, separation is they don't tend to kind of collide with each other. They don't tend to.
Okay, they
fly
keep
very
distance.
close.
All right.
Yeah, maintain a distance.
Okay, and
cohesion is they don't go too apart.
They keep the angle, you mean?
Yeah.
All right.
Angle.
Okay.
Yeah, they keep the angle.
Mm-hmm.
So, by doing these three things, what actually they're doing? This looks very simple, but the problem they solve is very complex. They maintain optimal group flight efficiency. A simple word, but ask from aerodynamic engineer how tough it is. Means people have to run simulations on maybe servers with 30 GB RAM for maybe 3-4 days to determine a optimal angle and flight speed for a particular plane shape for a delta formation. And how they do it? Somehow they know that the optimal shape for group flight efficiency is V formation. No human beings know it because of simulation. So that's why in air shows you see, or even in kind of wars, when there is a group of planes, they tend to maintain this formation because this saves them a lot of fuel. How it saves them, if somebody is interested, I can go, but if not, then assume that this is optimal formation for group flight efficiency. And to maintain this optimal formation, is if the planes are flying, pilots have headphones, they're talking to each other, and they're looking at the speedometer, altitude meter, and accelerometer to maintain a hell of parameters and need years of training. But they do only 3 things, and they are able to maintain this V formation. How? Unfortunately, there was an interesting slide which is not here, but okay. Oh, I think I should show that slide. Okay, no worries. Means if we transform their okay, yeah, this slide is it. Yeah, means if you look deep into the biology of their evolution, the problem somehow inherently they know the V formation is optimal. Nature somehow tells them, and then by nurture means they need to practice to do this, and that's why you'll see that they are not always flying in perfect V shape because this comes to nurture. But they are trying to fly in V shape. They are not. You won't see them trying to fly in another shape because somehow nurture. This is inherent, and this is trained. So means that's why I was saying means nature plus nurture makes them do this. And okay, so based on that observation, we see that okay, if we try to get the abstract idea from there, the birds had an objective, okay, and somehow they transformed this objective into a simpler objective. You can call it goal for sake of having a different word, and they were able to achieve this goal with this local behavior. You can call it functions. So SO functions, SO goal, and SO objective. And nature helped them to transform the objective function into SO goal and SO goal into SO function. But nature won't help us here, so we need to have our traditional tools which we rely. Okay, let's go back to our example. This is our system model, and this is the statement of the problem birds face. A flock of common cranes wants to self-organize its flight attributes and fly such that the average flight efficiency in the whole flock is maximized by minimizing the average air drag. Okay, look at this table, and while you keep looking, see this magic. You just need to swap the terms. Air drag means interference, spectral efficiency means flight efficiency, fly means operate, flight attributes means antenna tails, and base station means common crane. And your problem is almost same.
All right, so it means we should give the operational rights of running an LTE network to a flock of birds. Is that what you're saying? No?
But I'm trying to say, I'm demonstrating the use of biomimetics. Means it's possible somehow, sometimes, it's not always possible, but sometimes you can do this. Okay, so once we have done this, it looks very easy, we have solved our problem, but it's not the case. Real world is not that simple. We need to first do the first step, identify our objective function. Means what is our objective? Objective, as I said, means we want to maximize spectral efficiency. To maximize spectral efficiency, we need to formulate actually antenna tails, spectral efficiency as a function of antenna tails. And to do that, here is how a typical SNR at a given point for a given user will look like in the network. It's a function of antenna gain, transmission power, and path loss, where antenna gain itself is function here. Ms. Nisa yesterday introduced this, but in three-dimensional space it will look like this. Okay, so if we put our problem in words, it's like maximize spectral efficiency in hotspot by optimizing the angles of all the N base stations in the system, but without sacrificing the average user throughput. Means the user outside the hotspot should not be sacrificed. So this is how the problem will look like. This is first step. We are identifying our SO objective. Just like the birds identified, okay, they need to maximize spectral efficiency. If we will do that, this is how it will look like. I have made clear all the notations just to keep you going with me. This eta here is spectral efficiency, which is a function of vector of tilt angles for all the antennas in the system. And we want to maximize the spectral efficiency. That's why we don't have bandwidth here, which is theoretical, you can say, capacity, ergodic capacity without bandwidth normalized capacity. And this optimization has to be done on over this vector, which is n. And n is as large as is the number of antennas in the system. For example, if you have 2000 antennas, you have 2000 parameters. So just by looking at this function, and this is the constraint. The constraint is saying that, okay, for all the users which are not in the hotspot, the spectral efficiency after the tilt optimization should not be lower than what it was before the tilt optimization. Okay, so this is constraint, and this is a problem. Just by looking at it, we can see that it's never going to be convex, and at the same time, it's very large scale function. So we have done our first step. We have a objective function, but we need to identify our SO goal. So what were the characteristics of SO goal? SO goal was something which could be broken down into SO functions, local SO functions, as the birds were able to achieve V shape by separation, cohesion, and alignment. So how we do it? I won't go into details. Oh my God, this is a mess here. Anyways, I think this is determination of center of gravity of user. Okay, I won't go into detailed mathematical proof, but this is a proposition. You can call it theorem. And what we are doing here is that we are proving that for tilt optimization, you don't have to optimize your tilt for each individual user, particularly if there are hotspots. Okay, if there are hotspots, then you can easily represent your whole cell users with a 1 point, namely center of gravity. Okay, and the proof for that is given here. You can calculate your point by solving this expression. And a little bit insight. The reason we are able to achieve this point is, means, for example, this tilt, whatever is the tilt, any particular tilt value can be translated into a locus of points. Anyway, it's not kind of 2D setup, two-dimensional set of points. It's just one dimension. Means it's always a locus. So you need to find that locus where your hotspot is located. If your hotspot is here, for example, for this particular tilt, means if the hotspot is there, then this should be the tilt value. This locus should be focused by your tilt. And to focus that locus, you can kind of easily find your tilt angle by inverse of tangent. But this proof, you have to go through this proof to understand how we are exactly calculating. This proof is actually, this is simple, but the reason we have to do this proof is actually we want to embed the constraint that the users which are in this area, they are not affected. So when your tilt is incorporating the center of gravity, it is also incorporating the fact that the users in this area, on the average user throughput in this area stays same. Of course, you will, if you lose some throughput for these users, you will get some throughput for these users. So your average will stay same. But since there are hotspots, yeah.
What if the distribution is uniform?
Yeah, I'll come towards that point later. I'll come towards when the distribution is uniform. Still, you need to have an optimal tilt.
Okay.
You need tilt is something, means you need to set some tilt. It can be 0, it can be non-zero. For uniform user distribution, it will be a different optimal tilt. And the advantage in that case is that you don't have to take the measurements to know the location of hotspots. You can simply still the formulation will stay the same, but you can simply calculate it as a function of area density. Then your cell area is actually telling you. So the geographical center of gravity.
It's like median.
Yeah, median. It won't be median exactly because median is actually physics center of gravity. Here we are talking about center of gravity in terms of tilt.
Okay.
Means the point which maximizes the focus of tilt. Okay. So that's why means the expression is same. Means you the same way you calculate the median of any geographical shape, but here you weighting your median with the function of SNR, which is for the function of tilt. Okay.
Can I do you have maximum tills, minimum tills, and all that? Is that all
Yes,
part
yes,
of
yeah,
the
that will
framework?
come,
Yeah.
that will come later.
And the summation is over all users, including those who interfere from adjacent cells, or how do you handle that?
No, it's over all users.
Over all
In-
users,
in-
right?
This particular means for every cell you need to calculate it. When you want to calculate the center of gravity in one cell, you need summation over only users which are in that cell.
Right.
Yeah.
But their gamma, I presume, includes the signal to interference and noise ratio.
Yes, the gamma.
Meaning every user, I mean, there's a complete dependency between all
Yeah,
base
of course, the
stations
neighboring
and...
cell. I will come towards means this. When you are calculating, for example, here the problem is we want to calculate a tilt which optimizes this gamma. Okay, using the user distribution in this cell. So your question was, do you need user distribution information for this cell or for all the cells? No, you don't need user. You just need to know the SNR value these users are receiving in this particular cell.
Yeah.
And that SNR value will actually incorporate the interference from other cells.
Where do you have the user distribution here mathematically in the gamma?
Means this X and Y, if you can see. This gamma is function of X and Y.
Yeah, but the gamma is a signal to noise and interference ratio, right?
Yeah.
So,
At a particular point.
yeah. Well, user K will have its useful signal from its own base station, the noise and interference from all the other.
Base stations,
Okay.
yes. So implicitly it's being taken care. But
So-
you need to measure the SNR values of that particular cell for which you need to calculate the center of gravity. Once you have calculated the center of gravity, then again when you will plug in, instead of this over all the hotspots, you will plug in those center of gravities into your formulation. Now you are assuming that okay, every cell is represented by cell user distribution is represented by a center of gravity, and this center of gravity is calculated based on the fact that what SNR each user was receiving,
Right.
and according to that SNR, what should be the center of gravity for which the tilt should be optimized.
So are you then optimizing the tilt for every single TTI or every second, every millisecond?
That's the question I will address in the last slides. First agenda is to have a solution. Then, based on the complexity or simplicity of the solution, we can identify its limits.
Yes.
What can be the minimum, maximum agility we can implement.
No, it looks very good. Maybe I would introduce some weighting, meaning you don't adjust all the time.
Yeah,
I mean, it's an electrical tilt, but still.
Yeah. Means
So-
if you see means in this formulation, that's why means we did not introduce fast fading, and we are relying on totally the geographical SNR, which depends on the tails. And the geographical SNR is this. We are trying to find an optimal tilt which will kind of exploit the situation that most of the users are concentrated in one particular area of the cell. When that's the case, and then in the morning, for example, they are here, in the evening they are here, they are offices, this is residential.
Well, why do you need the pathless models at all? It seems like you're using, I mean, what you need is a feedback SINR value, the CQI values, or whatever, the channel quality values.
In the practical implementation, you won't need that, but when you are doing the analysis for modeling, you need pathless here.
Okay, I see.
Yeah, when we will come towards implementing this solution, this becomes more simple than the analysis.
Yeah, exactly,
But
yes.
this whole analysis is
Okay.
required to prove the advantage of the solution.
Okay, thanks.
Okay, so what we are able to do here is that we are able to simplify our problem into a SO goal, which looks like this. Means instead of from tilt optimization's point of view, if you are a base station and you have to set your tilt, you don't have to look at all the users. You have to look at the center of gravities, which you could calculate based on the SNR measurements if the user distribution is non-uniform, or based on the size of cell and your own tower height if user distribution is uniform. So once these points are known, then your optimization problem has actually squeezed over this summation. This summation, the length of this summation has squeezed, because here we had as many summation terms as users, but here you just have as many terms as number of cells. So, but the problem is still as you see, it's still a convex problem and still it's a large scale problem because your optimization variable hasn't gone anywhere. It's still very difficult to optimize it over all the base stations. So here we bring in again the philosophical argument, and we support it by some analytical insight as well. Again, you have to look at the paper to see how it works. But the idea here is, if we go back to our bird example, they don't tend to have foots and scales and kind of exact instruments to measure the exact angles. You'll see them, they are flying only roughly in a V formation. But just by flying roughly in V formation, as I mentioned, they are able to achieve almost 70% gain in spectral efficiency. And the interesting observation here is that they are just able to, if you read this paper, you'll see that they observe only their two immediate neighbors to determine what should be the separation and cohesion and alignment they should carry out. They are only, this bird is only able to observe these two neighbors, line of sight. Yes, this compared to a single bird. It's group flight efficiency. It's just like, if we had one base station, we never need to tilt. We'll have no interference. So it's systematic, holistic view, which gives you the problem, and then you need to find a solution. So we, inspired by this observation, we look at our system and we see that actually we have a similar scenario. We have two neighbors who are the most troublemaker neighbors. The rest of the neighbors, of course, they will cause you some interference. But if you do some simulation, numerical analysis, you will see that tilting does not propagate much beyond kind of neighbors, because signal bounces up. If, for example, let me explain. Yes, if you have tilted it down further like this cell and this cell, you can at the most kind of affect this cell. Okay, but after this bounce up. So the neighboring cells, particularly if there are cells here and here, they won't be affected. So only these two cells by affected the most. It's not that means they won't be affected, but these two cells would be affected the most. And since we observed that by observing only the two neighbors, we could achieve some, birds could achieve some flight efficiency. So let's see if we could achieve some gain as well. The reason is obvious, this problem, even if you are able to formulate it, it's useless. But okay, so we introduce this concept of triplet of cell. Triplet means each triplet should behave independently. Within the triplet, the base stations can cooperate. For example, in this particular triplet, when optimizing the tilt, the base stations will take into account the SINR, which is a function of tilts of rest of the two base stations only, not all the base stations. If that's the case, then our problem becomes this. This cap here shows this SNR is not anymore a function of all the tilts, but just two most neighbor tilts. And some analysis, in some analysis, you'll see that actually the beta is the sensitivity parameter here, path loss exponent. If you have a path loss exponent high, this is going to be actually very close to this. Means if you put infinity, it's going to be exactly same, but for a large beta, it is going to be, and large beta starts from anything above 2.5. So which is very practical in urban areas or even in suburban areas. So what you're going to exactly do is, you're going to assume that your system is consisted of a number of triplets instead of individual cells, and within each triplet, now you're going to execute this tilt optimization. So mapping it back to our example, So we were able to identify the objective. We were able to simplify it by the center of gravity theorem into a simpler goal, V formation, and we are able to identify, achieve that V formation approximately, and we are expecting some gains. Before expecting some gains, we need to solve the optimization problem we had. Now the optimization problem is only a function of 3 tilt angles.
We are assuming sectoring of
Yeah, of course, sectorization is there. Of course, sectorization is there. So now, unlike the actual problem, now our problem is tilt optimization over a triplet only, each triplet, and this is constrained. But again, this is how it would look like even for 3 cell triplets. And means what I have done simply means I have plugged in, this is the expression we need to optimize over tilt 1, tilt 2, tilt 3. And this constants are further expressions of vertical beamwidth. And these, so you see, this is again, it's not kind of it's not convex. But fortunately, since it's a small scale problem, it's not a large scale optimization problem here. So we are able to invoke some classical non-convex optimization tools. Particularly if we, as we all know, if we have a very small scale problem like just 3 optimization parameters, you can use sequential quadratic programming. But what is interesting here is there is an optimal point here which gives you a substantial gain in terms of spectral efficiency, which can be as high as 1.5 bits compared to roughly or unoptimally cell tilts or means arbitrary cell tilts. So, if you think in practical terms, you are not happy with the fact that it's a non-convex problem, then think practically and you can simplify the problem. In practice, tilts are never set. It's not practical, means it's not useful to set the tilts more than 30 degree. So you'll have just 30 into 30 into 30, 900 possible values, and you can search in 1 second on any laptop. So by doing this, you can achieve this gain. Now it comes to evaluation of this solution. These are simulation parameters, system level simulation. Messinissa explained it, how it works yesterday. These are the parameters we used. And based on that, means before going to the system level simulation, again some numerical results which show that, okay, if the hotspots move their locations.
One question.
Sorry.
When you said the tilt is a maximum 30 degrees, maybe I didn't realize that, but how is this tilt defined? In which direction 30 degrees?
Direction from the horizontal.
So horizontal is 0.
Yeah.
And
If you make your tilt even more than 30 degrees, depends on your radius. Means you're gonna serve just by maybe your neighbor. Means if I'm a base station and I have a height of say 20 meters, which is very large, even if I have a height of 20 meters, if my tilt is 30 degree and I have a vertical beam width of 10 degree only, so I'm gonna serve maybe up to this distance only. After that, my antenna lobe won't be focused. Okay. They will be on the kind of attenuation side of antenna, not on the bore side of antenna. You understand my point?
Yeah, it just, so 0 degrees is straight to the horizon.
Yes,
and
straight
30
horizon.
And plus degrees is down.
Yeah.
Okay, thank you.
Yeah, plus degrees. Yeah. So what we are seeing here is, means for different locations of center of gravities, which can be hotspot, which can be relay stations, and which can be, by the way, femto cells as well. If they are femto cells, you can use the same solution to minimize the interference. Means instead of your maximization problem, solve the minimization problem, and you can means minimize the interference. But assuming that these are center of gravity, in the first scenario you see that, okay, for this particular locations of hotspots, the optimal tilt values are 8 degree and 16 degree. I have fixed the third tilt value because it's not possible to show a four-dimensional graph. And the other set of locations of base stations, the tilt values actually change. So this shows that you have to actually, and this is what happens this side. If you look at this side, this happens in the real network. Means the hotspots keep changing the location of our day and night, our weeks, and weekdays and weekends. But as Misha said, means operators don't change their tilts that oftenly. They cannot, and it's not technically and commercially viable to keep changing tilts at this frequency. But when they are not doing so, you can see they are losing substantially, even with this distributed solution. Okay, in terms of looking at the overall system performance, here we are comparing it with the number of values. As I said, means 30 is the maximum practical value you'll ever find. So we are comparing it with different values of tilts. And we're plotting in self-organization. This line is tilts with self-organization. And also, we are not only plotting throughput at hotspot users, but also non-hotspot users. What you see here is these two lines, the black lines. Means for hotspot users, you have more gain. For non-hotspot users, you don't have that much gain, but still it's much better than those typical tilting mechanism, which are manual and also kind of arbitrary. So you gain, it depends on the location of hotspots, but on the average, means in this simulation, the hotspots are randomly located, and it's a 51 cell network. So you can have some substantial gain in spectral efficiency just by adjusting the tails of 3 adjacent base stations. And if you want to look at the numerical values, then this is how it would look like. Compared to no tilting, you'll have almost 45% gain. And compared to, say, traditionally optimal tilting for that particular network layout, which your ordinary planning tool will give you, you will still have 15% gain. But the problem is this is not about the amount of gain. It's about the amount of money, amount of quality service, amount of time, or amount of labor you would be able to save with a solution like this. Because you don't have to rely on planning tools and engineers to go and keep changing tails. You just need to put this solution in your base station, and then they're going to do the rest. Okay, this is the summary, how we solved our problem by biomimetics. Okay, and this is showing me this. If you replace your user distribution with outdoor relay stations, and you have to optimize spectral efficiency on their wireless backhaul, the problem even becomes simpler. You don't have to invoke the center of gravity theorem. You can simply use the triplet concept. For details, you can refer to this paper. Yes.
Okay. You showed these 3D graphs before, and you said, yeah, it becomes faster to simulate, but how long does it take to get these simulations?
If you just guess, means how long it will take to
Yes.
find the optimal values if you have set of 900 values only for any computer.
No, but I assume. You said you don't think about small scale fading because you have random channels.
As Misha told, and I second him, and I wanted to comment at that time. For operators, small scale fading does not exist. Particularly if you're talking on the scale of days and nights, hours, small scale fading does not exist. Because try to understand. Means as we received some presentation on propagation path loss model, you remember. So there is a path loss. Okay. On top of that we have shadowing, and on top of that we have fading. Okay.
Yes.
So what we are trying to do through this solution is that here is our base station. It had some antenna, and we wanted to set this tilt value which would optimize the average spectral efficiency of all the users or average efficiency of users concentrated on any point. Okay, so irrespective of whatever, means if the users were here, they were already getting say 2 bits per second. If they are here, they were getting 1 bit per second because of shadowing and pass fading and path loss. But if you have your solution in place, this will give you an increase on top of that, irrespective of because you are not changing power, you are changing actually your antenna. So whatever is the fading, even if there is a fading, you will get a boost, because by changing your, if your hotspot users were here but your antenna was focused here, if you have fading, it will have worse effect. Okay, if you don't have fading, yeah. So fading is not a kind of fading will ride on top of this solution always. This solution will float, keeping fading on top of it. Yeah, because scheduling, we are not playing at scheduling level. We are playing at antenna's physical parameter levels. Okay.
Just a question on that. Where's the this element of self-organization there? I mean, you're taking essentially local. Well, I have not 100% yet understood where is really this SON element there.
That's a good question. But that's why I defined SON in the beginning. It should be taken from functionality point of view.
Okay.
So what we are trying to do, we are trying to remove the manual intervention operators need by automation of the processes operators are following at the moment. Tilt is one of them. Okay, and we are providing a solution which is distributed. Okay, and which can automate that process. How it can automate? I have to I think go towards my first contribution. Maybe next contribution.
Yeah, where the equations are. So what you need to do is in every base station you need to run the linear programming thingy to solve the non-convex capacity equation. That's what you need to do.
Yeah.
Okay.
Yeah.
And this is basically assuming that the path loss which is in the cell is obeying the laws you presumed.
No. Means whatever is the path. This shows that if this is the path loss, the path loss function, we have a optimal tilt value.
Okay. Yeah. Okay. No, I understand.
Yeah.
I just want to know.
Yeah.
Okay.
And if the path loss model is different, the gain will change in value, but still there will be gain, because it's very obvious. Means at the moment we don't play around with tilts, and even if we play around with tilts, we don't optimize them jointly. It's not like that. If we change this antenna tilt for some reason, we are going to change neighbor antenna tilts optimally according to that. But with this solution, what will happen is that means these three base stations just need to have their CQI values of users along with their user locations. If there is a hotspot, they need to identify, okay, these are the hotspots, and they need to update it. So this update can be event based, it can be periodic. Okay, but if you want to look at the amount of signaling, this solution does not need additional signaling because you already have CQI reports. So based on CQI reports and user location, which I'll introduce later how we can have that and why we need this in future cellular networks. So we would be able to identify the spots, and those spots can be used to execute that solution, this solution. Yes. So this is, and since it's a distributed, it's autonomous and scalable, agile, and stable, so it's on. Yes.
It still works. Right. Yes. Question. It may do funny things because I think we're running out of battery.
How does this solution relates to beamforming scheme in which you just have maybe 2 antennas and you can digital shift the beam?
That's a good question actually. This solution, if you give you a straightforward answer. It has nothing to do with beamforming. Beamforming is something separate. Beamforming assumes that you are actually able to shape the pattern of your antenna. You are able to have multiple lobes of the antenna. Okay, and this solution assumes that you have only one lobe. Okay, but if you want an advanced answer, the advanced answer is that beamforming in general actually plays with the azimuth of antenna. Okay, but this solution is about the tilt of antenna. If you even have a beamforming solution, still you can implement this solution because this will keep the tilt optimal all the time. Getting my point? Yeah, done together. But I haven't done it yet. But means
yeah, but beamforming will be more flexible, no? Because you don't need to move physically anything.
Beamforming, and let me ask you a question. Beamforming assumes that there are 1 or 2 users in the center, yeah?
There are what?
1 or 2 users, 3 users in the center, few users.
Well, any users, as long as you have
No,
2 antennas or more.
Means practically, I'm saying practically. And means I never said that this will need a physical movement of the antenna. Tilt can be done electronically, it can be done mechanically. By, I think, UMTS, every base station is capable to adjust its tilt. That's why I put that remote parameter update. That was particularly with respect to tilts. Tilts are nowadays being changed electronically, but the thing is, there is no proper mechanism to optimally set them. They are usually set by thumb rule. Because the 10 years engineer with the 10, 20 years of experience says, okay, this is urban area, this is cell size, and okay, we have 10, 20 plazas there, so okay, let's go with 3-degree tilt. Yes, one beam. One beam. If you have more than one beam, then still you will have tilts for all of them, yeah? Means beam, when you say beam, that's what means there is confusion. When we were having a presentation by Moon and even Missinessa, both of those antenna models were 2-dimensional models. They were not 3-dimensional models. To imagine tilt, you need to have 3-dimensional model. Beamforming, when it's done on the horizontal plane, yeah? Okay. Yeah, even vertical means if your user is close, yes, it's vertical. This solution, if you have beamforming, then all the problem is solved. You don't need to have this solution, but still you can have this solution. This is again, means I did not emphasize on this point, but for example, if you look at the white papers of Motorola or NEC or NSN, you'll see that they have constraints like this. They don't even have the freedom to change the operational processes of operators when designing SON solutions. It means the SON solutions they provide should not be such that means they have to change the routine processes of the operators. So with the existing procedure, operational procedure, this solution is meant to give you some quality of service by removing extra labor you needed.
Okay, yeah, just my point was you can use both then, beamforming and this.
Yeah, you can use both.
But still I believe beamforming will be more flexible because you don't need to
of course it's
mechanically or
obvious.
electronically
It's
change
not rocket
anything.
science. It's very obvious.
Yeah.
If it's just like it would be saying like, okay, Volvo would be faster or Ferrari would be faster, so it's very obvious which one would be faster.
Yeah, the tilting is usually also used for coverage and interference control.
Yeah,
so maybe, if you tweak another matrix, not the capacity matrix, which is rather where the beamforming goes in, you get the good complement. But it's a good example of two SON functionalities, the beamforming and the tilt, maybe, giving contradictive instructions to the beamformer.
Yeah.
Yeah. So then you need to decide whether for you it's more important to keep coverage and minimum quality of service in place, or whether capacity to a specific set of users is more important. Yeah. Okay, let's have a break now before you come to the load balancing, and you know, we have our coffee break. Take it easy, and then we continue in the after the coffee break. Now, before we break, just a reminder: whoever comes to the or registered for the social event tonight, please come to see me. I have tickets which you must not lose. Okay, otherwise I cannot get you into the whole event. We are going to this restaurant. Well, we are going first with the bus at 7 o'clock, leaving down there where the barrier is, okay? Be on time, the buses will not wait, okay? So please be on time there, 7 o'clock, and we leave to the castle. The mayor's going to receive us, and then we go down to the beach to have some fun. And what else? So yeah, please take the ticket, don't lose them. All right, thanks.
We have to turn it off. Excuse me. Oh yes.